Here's the ionosphere, 30 to 260 miles above the surface. Radiation from the sun will momentarily strip electrons away from the parent atom in the upper reaches, creates ions, and this is the ionization. The ionosphere is a region of the atmosphere extending from as low as 30 miles to as high as 260 miles above the surface. So, we've got a space station up there. Where is that orbiting? What's the altitude?
About 250 or so. I would say it's about 230 or so.
And generally, if we put up, when we put up this space shuttle, it would generally orbit miles. So that gives you an idea of what's going on. When we put up a low Earth orbit satellite, solar radiation causes atoms in the ionosphere to become ionized. The ionosphere organizes itself into regions or layers. D region disappears at night, and that the D region is the lower one, and that absorbs high frequency signals during the day, and it's why 80 meters doesn't work very well during the day.
That's wide open at night?
It disappears at night. So the ionosphere organizes itself into regions. D region disappears at night. The E region also disappears at night. This sporadic E happens during the day and during different times of the year. The F region splits into F1 and F2 during the day. The ionosphere acts as if it's an RF mirror. It isn't really reflecting, it's refracting as a mirror. The ionized layers of the atmosphere actually act as an RF mirror that refract or bend certain HF and VHF radio waves back to Earth. Skywave propagation is responsible for most of the long-range, over-the-horizon communications. So, this ebbs and flows depending on sunspots. Right now, we're coming into a sunspot high in the 11-year cycle of sunspots. That produces more energized ions in the ionosphere and better propagation. It also produces flares and it creates blackouts. So lots of things going on right now. So here's the layers. D layer, E layer, F layer, and F2. So the F2 layer is the highest one, and it means that signal goes farther than the signals off the lower layers.
In one galaxy.
So the density of the atmosphere has effects, the intensity of the radiation that can penetrate to that level, and the amount of ionization that occurs. There's so many variables. The sun is the big variable, and how close we are to the sun and how much our latitude tipped towards the light. How quickly the electrons recombine with the nucleus also has an effect.
Okay, before you move on, go back to this. You guys can't see some of this from where you are. This says signals with increasing frequency. So this is a low end HF, mid HF, high HF. This guy right here is actually a VHF signal. It says right there that signals above 100 megahertz.
They go straight out through.
Yeah. Right here, this says higher frequencies can pass through the lower layers. So that's what we're talking about there. The higher the frequency, the more it's going to go upward. Beyond a certain point, it's simply not coming back.
So that varies with the angle at which the signal refracts off of that layer and also the frequency. So you have a maximum usable frequency, but sometimes you can manipulate that a little bit by aiming your signal right at the horizon. So D layer region is the one at the bottom, right there, and that's the absorption layer. So D layer doesn't do anybody any good unless it disappears. It does disappear at sunset and reforms at sunrise. Absorbs long wavelength radio waves. Primarily affects 160, 80, 60, and 40 meters, mostly at 80 and 160. So the people that are running nets pretty much every night, I'm on the Oregon Emergency Net, 80 meters. At this time of the year, we don't have any problems at all. We can cover the state. Midsummer, Okay, it's 6 o'clock, the sun is still up. It's still maybe 2 hours before sunset. So that D layer is still quite active, and it becomes a problem hearing stations even across the state. Closest to the Earth's surface. And since most of your nets are not long distance nets, most of your nets are regional, either statewide or West Coast, regional nets like that, they're using 80 and 40 meters. They're not on 20. The E layer, one hop up to 1,200 miles, similar to the D layer, lasts longer into the night, less absorption, and you get sporadic E skip. Occasionally strong over-the-horizon signals on 10, 6, and 2 meters. E layer can be a lot of fun, and they call
You can hold
6
still.
meters the magic band because it doesn't take much of an antenna, it doesn't take much power. On 6 meters, if you're using sporadic E, you can make contacts up to 1,200 miles or so. And the F layer, these are the important ones for long-range propagation on the HF bands from 80 through 10 meters. One hop up to 2,500 miles. So 2,500 miles, that's all the way across the US. That's a long hop. Generally, it's 2 hops from one coast to the other. If you're over here, I can generally get across to Chicago or somewhere in there without a problem, because that's one hop. But to get to the East Coast, I don't hear that much, especially at midday. It's much easier to go across the Pacific and work Asia from here because we're so close to the coast. If we go the other way into Europe, you've got 2 hops over land before you even get to the Atlantic. So it gets really
It's
dicey.
pretty well absorbed and gets pretty nasty by the time
Yeah.
it gets to the ocean.
Going over the pole to Russia and Eastern Europe, it's possible, and sometimes it works.
Sometimes it's the only way you can get there.
So the F layer is split into F1 and F2 during the day, and that means you've got a lower propagation off the F1, doesn't go as far, skip via the F2, is longer via the ionosphere region. F layer, dawn to just after sunset. During the sunspot activity is the best time for long distance 10-meter propagation via the F layer. But again, the F layer might go away. But even in the F1 layer, we're talking about the F1 layer. Yes, 10 meter takes a pretty high energized F layer to propagate. 6 and 10 meters may provide long distance via the F layer during the peak of the sunspot cycle. And we're getting into that now. Reflection and absorption. Radio waves are refracted or bent in the ionosphere. The stronger the ionization level, the more the waves will be bent. The shorter the wavelength, the higher the frequency, the less the waves will be bent. VHF and UHF are only slightly bent and almost never enough to return to Earth. So generally they just go right out through the ionosphere and don't come back. UHF signals are rarely heard beyond the radio beacon because they're usually not propagated by the ionosphere. Now they have websites that you can go to that show in real time a propagation path. So it'll have the world map, you can focus in on a smaller area, you can filter that down to a specific band and look at the 6-meter propagation between here and Asia. And you can look at somebody making a contact and it will list the 2 stations.
Like all night.
Yeah, so somebody has made a contact, and as soon as they make a contact, they go to this website and they type in who they contacted and at what time, and it comes up on the map. Very cool stuff. Now we have a lot more at our disposal. So the critical angle is the highest takeoff angle that will return a radio wave to Earth under specific ionospheric conditions. So we got the F1 layer up here. Okay, I want to contact this guy over here. So that skip angle is like this, and at 6 meters, that won't skip. It goes right out through the ionosphere. Now, so let's try 10 meters. And it goes right out through the ionosphere. Okay, we're going to try 20 meters. 20 meters is skipping. So it'll depend on the frequency and it will depend on the angle. If he's further away and we try an angle that's not quite as steep, maybe 10 meters works. So it depends on the angle and it depends on the frequency.
As the sun goes down, you go to longer frequencies, basically.
So that's the critical angle I was just talking about, the highest takeoff angle that will return radio wave under specific operating conditions. Critical angle decreases with increasing frequency.
It's like it's all a roll of the dice.
Well, it can be.
No, it's
It's
not.
also, but it is
You
predictable.
just gotta load the dice. Yeah, you can predict it pretty well. I use a couple of websites that give me information about the solar flux right then. So even before I check into the OEN in the evening, I look at what the solar flux index is and if there's been any recent flares. If there's a flare ongoing right now and I don't hear anything on the band, I know what's going on.
Turn your radio off.
Yeah,
Yeah, pretty much.
it's not my radio, it's the band is dead. One reason why low angle of radiation is important for working DX. Just demonstrated that the angle of radiation is lower. It's just like skipping a rock off the surface of a pond, right? You aim at a high angle, that rock right down to the water. Get it at a low enough angle, and it'll skip right off the water. This is very similar. So the critical frequency, the highest frequency, which is refracted back to Earth at a given incidence angle. Reflection and absorption. Absorption in the atmosphere is denser at lower altitudes, causing part of the arc energy to be absorbed. So somebody mentioned moon bounce. Doing moon bounce, it's a trade-off between using a high enough frequency so that you can build a big antenna with a lot of gain and dealing with the absorption in the atmosphere at that higher frequency, which lowers your throughput. The trade-off actually is somewhere around 2 meters. You get higher than that, you've got more absorption in the atmosphere, especially when the moon is low, you're going through a lot of atmosphere, and 440, you lose too much in path loss. It's a trade-off. The longer the wavelength, the frequency, the higher amount of absorption. Absorption in the D region, almost no refraction bending of radio waves. It's the most absorbent of signals below 10 megahertz. So we're talking about 40 meters and 80 meters, 160 meters. It really absorbs a lot. The E region has more refraction than the D region and less absorption than the D region. So here's the physics.
And this is a pretty good slide.
Yeah. So you're looking at what happens to a signal at a high angle of incidence, right there. At a high angle, it can't see enough refraction and it just goes on out. And at a little bit lower angle, now we're bumping into more of these little ionized particles and you start to bend back towards Earth. Even lower than that, and it just scatters and doesn't go anywhere. Skywave and ground wave propagation. So skywave is off the ionosphere, ground wave doesn't go up that high, it just uses the curvature of the Earth.
And this is one of the things that makes a beam antenna kind of fun to have, is because you can select if you want to use a skywave or a ground wave using the angle of the takeoff angle.
Yeah, that has a lot to do with it. If you're using an NVIS antenna, a near vertical incident skywave antenna, most of the signal's going straight up. You're not going to have much of a ground wave signal. And I find this really true when I'm on a local net just the southwestern part of Oregon, and I can hear stations on the very far coast of Oregon, but I may not be able to hear somebody in Grants Pass. And what I'll do is I'll switch antennas real quick and go over to my vertical. Now I can hear the guy in Grants Pass, but I can't hear the guy on the coast. And I'm seeing ground wave off that vertical because all the signal is close to the horizon. But because it's close to the horizon, I'm not getting skywave at a high angle, so I don't hear the guy on the coast. The skywave is refracted radio waves back to the Earth. This is the ionosphere. Each trip from the Earth, this is kind of review. On the hop, multiple hops are common. Maximum distance of a single hop depends on the altitude of the region where the refraction takes place. The E region of single hop could be up to 1,200 miles. F2 region, single hop could be up to 2,500 miles. And you'll need to know those distances, but in reality, it's quite a bit less than either one of those. Hops considerably less than the maximum distance are called short skip. Short skip is a good indicator that skip is possible on a higher frequency band. So you could go up a band and maybe get even further. Fluttery sound result of irregularities. Maybe that's just a high energized region. Maybe it's aurora. Irregular fading of signals propagated by the ionosphere are likely the result of random combining of signals arriving via different paths.
And you'll hear that a lot. You'll hear a station that'll be really strong, and maybe you're talking to them, and then they'll fade out to where either you can't hear them, you can barely hear them, and then they'll come back again.
Radio waves that follow along the surface of the Earth are ground wave. So you're using primarily vertically polarized and ground wave. Loss is created by proximity to the Earth's surface, cause a rapid decrease in signal strength or increase in distances. Higher frequencies equal higher loss. Skip distance is the distance from the transmitter to where the radio wave first returns to Earth. The skip zone is too close for skywave propagation, but too far for ground wave propagation. So I may try to go up in frequency and it doesn't work. So that gap layer
What's these
right
shots
here,
showing?
that's the skip zone.
This right here is your ground wave propagation.
That's ground
area.
wave.
This is your
And that,
skip zone
that
propagation.
there is skip zone.
So there's no way you're gonna hit that little area in the skip zone. You
Right.
just- You just won't.
This spot right here, you can't get there.
Not unless the propagation begins to change.
Right.
Well, like when?
Yeah. So, short path is the direct route between stations, shortest distance. And the shortest distance may not be logical. The shortest distance on a globe may not be the way we think. So San Francisco is directly south from here, but that may not be the shortest distance. Long path, 180 degrees for the short path. So there's short path from one side of the country to the other. Long path is all the way around the Pacific and across Asia and across Europe and then across the Atlantic.
Notice the arrows. This one is pointing to the right and it stops here. That's your short. This one is indicating to the left and it goes here, picks up here and goes all the way back there.
And that's that
That's
delayed
because it's over
echo.
water.
It certainly is.
Yeah, and it only takes like a quarter of a second to make that path around the globe. Long and short path conditions may not support short path, but long path may be possible. And vice versa. Usually it's the other way around. An echo indicates both short and long path is open. Long distance ionospheric propagation is far more common on HF frequencies than on VHF and higher frequencies. So this has to do with maximum and the lowest usable frequency for signals to be refracted.
And now we're going to get into something that you're going to have to just take our word for it, okay? The maximum and lowest usable frequency are coming up next, and just listen up. This is
Maximum usable frequency, MUF, is the highest frequency that will allow communications between 2 points. So, get back to our two little guys here over the horizon. We tried it on 20 meters, that works. We tried it on 10 meters, that didn't work. So that makes 20 meters the maximum usable frequency between those 2 points at that time. Maybe later in the day, it works on 10 meters, but at that time, that's your maximum usable frequency.
And it will change.
it's very fluid.
Radio waves on frequencies below the MUF will be refracted. So we could move to 40 meters and it would work on 40. We could go to 80 meters. Well, maybe if the D layer didn't absorb too much of the 80 meter signal, it might work on 80 as well. Above the MUF will be lost into space. Lost in space. For the least attenuation, for long distance skip, propagation used the frequency just below the MUF. And this is the ticket. This is just like that rock skipping across the water. You're looking for that angle that just makes it. Lowest usable frequency. Lowest frequency that will allow communications between 2 points without getting absorbed in the D layer. And the radio waves on frequencies below the LUF will be attenuated before reaching the destination. And that's in the D layer, in the atmosphere, get absorbed. When the lower usable frequency exceeds the maximum usable frequency, propagation via the ordinary skywave communication is not possible. So it means there's too much absorption and it's not going to work. Usable frequency. Frequencies below the maximum usable frequency and above the lower usable frequency get refracted back to Earth. So in between, that's like the 20 meter, 40 meter, 80 meter. The in between, if it's too high, goes out into the ionosphere. If it's too low, 160 meters, gets absorbed. Only in that bracket.
And this is one of those preferential statements that is almost guaranteed to be on your general exam.
Scatter characteristics. What do we mean by scatter? Localized areas in the ionosphere that can reflect radio waves as well as refract them. We talked about sporadic E earlier, and this is an example. Direction of reflection is unpredictable. Yep. Especially when you're either at or maybe just above the maximum usable frequency, and you're not hearing anything in the band. The band is dead. So you're scrolling along from one end of the band to the other, and suddenly you hear this station in there. Well, it doesn't make any sense. They're usually well beyond where you hear the short skip. And it's probably sporadic E, but it may be on 20 meters. You don't usually do sporadic E on 20 meters. But you're only, and you hear more than one station, and they're all in the same area. You know, you're hearing stations out of maybe southern Illinois, and okay, I've just worked at station in southern Illinois. Here's another guy in southern Illinois. What is this deal in southern Illinois? Well, you've got this one little cloud up there, this little E-skip cloud, and between you and him is this path, reflected path. No other path is going to work to your location, only that one path. And then it goes away, and you don't hear anything anymore. So it's just the idea that direction of reflection is unpredictable. It could be in direct line of sight in the path, or it might be off to one side. Reflected signals are much weaker than refracted signals. I mean, guys have done 2 meter and 440 reflected signals off of an airliner at 30,000 feet. So it doesn't take a lot. Of course, that doesn't last very long. Pretty soon it's out of sight, but it has happened. Allows propagation above the maximum usable frequency if you're using scatter. Yeah, so backscatter.
By the way, we have a slang name for stations like that. They're called alligator stations. All mouth and no ears.
So scatter modes. So you might have scatter that's physical. Maybe you've got a mountain here, and you've got a signal that goes out and backscatter coming off, and somebody over here is picking that up. That's reflection scatter. There's also scatter right off the top. We talked about that. That's refractive scatter. HF scatter signals often sound distorted as energy is scattered into the skip zone through several different paths. And HF scatter signals in the skip zone usually are weak because only a small part of the signal energy is scattered into the skip zone. Okay, NVIS. A lot of people are using NVIS antennas because they're easy to put up and they're functional in that they provide communications statewide. At frequencies below the critical frequency, signals arriving at any angle are reflected. The trick is to select a frequency below the critical frequency, but high enough that absorption of D region is not excessive. So for instance, in the statewide emergency net is using 80 meters because most of the time D region is not going to be getting in the way at 6 o'clock at night, except midsummer. And then, so that it's below the critical frequency, but not high enough. Use a horizontally polarized antenna on 1/8 to 1/4 wavelength above ground. Why 1/8 to 1/4 wavelength? So if you have an antenna that's above a half a wavelength, more of that signal goes out on the horizon and less of it is going up high. For a near vertical incident, we want the signal going fairly high angle because we want it to come down within
As
200
an umbrella.
miles.
Think of it as an umbrella.
Yeah, we don't want it to go 2,000 miles away, but we want it to come down within a couple hundred miles. So to make that happen, we need the signal going up maybe above 45 degrees. That means we need to get our antenna down low and it can wave to a quarter wave above ground. So it's not, that's usually, it's not a hard thing to do to get it 1/8 to a quarter wave because you, and an 80 meter antenna is a long antenna, 120 feet or more. To get that a quarter wave above ground, what's a quarter wave at 80 meters? Half a wave is 40 meters, a quarter wave is going to be 20 meters, a meter is 3 feet, 20 meters is 60 feet, so a quarter wave would be 60 feet above ground. Well, that's probably as high as most guys are going to get, and that's still considered an NVIS.